Our work is on online distribution shift detection via recency prediction. Distribution shifts may lead to catastrophic failures for learning-based systems, so our goal is to detect distribution shift quickly before failure occurs. In a streaming fashion, this is useful for robotics where data comes in online, and with guarantees limiting the number of false alarms, because if there are too many false alarms, the warnings will be ignored by the user and not useful in practice. And we'd like to do this for gradually shifting episodic situations. For example, for an airplane that repeatedly taxis down a runway, there could be gradual distribution shift over time due to sensor degradation, and we'd like to issue an alert before a problem occurs. Here's a high-level overview of our method. We target safety-critical robots, for example, an autonomous aircraft using a deep neural network for perception to taxi down a runway. In this example, the DNN used for perception is unreliable under distribution shifts. For example, when training data contains daytime images and the system deploys at night, perception errors can cause dangerous system faults. So to improve safety, we design a warning system that detects distribution shifts. And we do so by training a neural network to predict which samples are more recent and issuing a warning when the neural network is consistently able to predict recency. Now I'll go over our method more concretely. Our approach is to design a test statistic such that if the distribution drifts, this statistic will grow and we'll know that the distribution has changed. And martingales give us a very good tool for designing such a test statistic. A martingale is a sequence of random variables m1, m2, etc., such that the expected value of mn plus 1 given m1 through mn is equal to mn. And they have this nice property formalized by Dub's inequality, which basically says that the probability of a martingale growing very large is very small. For example, the probability that a martingale starting at 1 grows larger than 100 is less than 1%. So here's what we do. We train a neural network model F to distinguish between older and newer samples. And we define an indicator variable that is 1 if F predicts correctly and 0 otherwise. So if no distribution shift has occurred, this indicator variable is a Bernoulli random variable with p equals 0.5. And we can define a martingale as shown here. The intuition here is that if your distribution didn't drift, your classifier should not be able to guess whether a new sample is actually a new sample better than random chance. And therefore, the probability that it makes a correct guess is 1/2. So we can define a martingale based on this, and we know that the probability that the martingale grows very large is very small. And that's how we can limit our false positive rate. I'd like to take a moment to talk briefly about how our work compares to prior work. So prior work is not learned at all and relies on a hand-designed score metric. A distribution shift warning is issued if the score metric starts deviating too much. Our work leverages modern neural networks and is end-to-end and learned. We directly learn whether there's been a distribution shift rather than checking whether a particular hand-designed metric has changed over time. And our method is self-supervised. We only require the input samples. We don't require any labels or score computations. Because our method is end-to-end, it detects shifts more quickly than prior work, and because our method takes advantage of learned networks, it can perform well on high-dimensional data such as image data. To validate the performance of our method, we use image data from an autonomous aircraft in a photorealistic flight simulator that repeatedly taxis down a runway. Here we have a gradual daytime to nighttime shift. This is a simulation of the airplane taxiing down the runway in the morning on the left and in the evening on the right. And this day to night distribution shift causes the autonomous aircraft to go off the runway, as we can see on the right. But with our method, we can detect this shift within 13 episodes, where each episode is the plane taxiing down the runway. And notice that the sky is not even dark yet after 13 episodes. And meanwhile, prior methods take much, much longer to detect this shift. We then look at a distribution shift caused by a small change in the camera angle. This could happen, for example, if the camera was knocked slightly askew. So we first change the camera angle very slightly, just that much, just a couple of degrees, and this small change actually causes the plane to go off the runway, as we'll see in this video. The inset in the top right is what would have happened without the shift, but with the shift, as we can see, the plane veers off the runway. And our method also detects this distribution shift. We can see from the plot that when there is a distribution shift, the martingale grows quickly, and when there's no distribution shift, the martingale doesn't grow. And we do find empirically that we have a very low false negative rate. In our experiments, every time there was a distribution shift, our method did in fact detect it. And finally, we tested our method in hardware using a FreeFlyer space robotics testbed. The FreeFlyer is a 2D mobile robot that floats almost frictionlessly on a smooth granite table, and this simulates zero-G or zero friction conditions in space robotics applications. We used this in our experiments to perform a visual servoing task that emulates autonomous spacecraft docking, where the docking target is the visual pattern defined by the International Docking System Standard for spacecraft docking adapters, and it's shown here. So our goal here is to navigate autonomously from the initial position to the target, and we gradually add corruptions to the visual target. Specifically, we add one additional white strip over the target after each episode. This setup imitates autonomous spacecraft docking at the space station, where each additional docking could chip some paint off the docking target. And the images across the bottom show what the target looks like initially, after 5 episodes, after 21 episodes, and after 30 episodes. So our method issues an alert at episode 21 before failure occurs at episode 30. So these videos show the FreeFlyer navigating to the target at episode 0 on the left, at episode 21 in the middle, and at episode 30 on the right. And we can see that it successfully navigates the target at episode 0 and at episode 21, but it fails to navigate to the target by episode 30. It veers off to the left. To summarize, we designed a warning system that detects distribution shifts on high-dimensional data rapidly and in an online manner. And through extensive experiments, we validate that our approach significantly outperforms prior work. Thank you.